Okay. Good morning. Welcome to Operating Systems. My name is Surendar. I go by my first name. Um, so, today I was going to give a brief overview of what operating systems are, what we hope to achieve in this class, and why you should care, and some guidelines on how we're going to go about in terms of gradings and all those things. But before I could even start, you saw what you have to go through, right? It took me like 5 to 6 minutes to boot up this darn thing to get the PowerPoint slides up, right? And there's no reason. I'm sure many of you may have faced the same issue. Your machine is not doing what you want to do, and many of the times operating systems are kind of in the way, which are either they can do make it look better, or they can be annoying, like what we had to face. So first, my office is there. My office hours are online. So if any of you have, some of you have taken my classes before, I'm mostly on most of the IM programs. I'm on Yahoo or AOL or Skype. So those are the easy way to reach me. Yeah.
Random question. What would be your screen name?
It's on my homepage.
It's on your homepage?
Yeah, I think my first name is my AOL one, iChat, and for Yahoo's Surendar Chandra, and it is on my homepage, right? So, and I'm usually on till late, so feel free to send me a text chat first before you call my home, right? And there's a TA, and TA will not have office hours. So one of the things I suggest is for homework projects and stuff, send an email to the whole class, if you have any questions, and maybe others in the class can chime in, or the TA or me can chime in. So that's some of the ways you can reach me.
Check if the lights. Is the little light on the receiver coming on?
Oh.
There should be on there.
Thank you.
Well, it doesn't. Yeah.
Sorry. So today we'll go through a little bit overview of what operating systems are, and talk about the course guidelines. The reason I kind of give overview is operating system is a core course, right? So most of you had no choice but to take this course, right? And most of you had no choice but to buy the book. I apologize for the book being like very expensive. I didn't realize it's gone from 60 or so for a few years back to now 135 or so for the new version, right? How many of you bought the textbook? Right? It's fairly expensive, right? Compared to the Mac OS X book, which seems like more bang for the buck because it's fairly big, whatever, right? So the textbook we have to use the textbook because the homework assignments and all use the textbook a lot. I've asked the library to buy a copy of all the 3 texts and put them on reserve, right? So they should be either now or it should be there soon in the engineering library, right? We will use the textbook fairly a lot. The recommended books and the suggested books are good books. Those are books that you may want to have. So if you're using Mac OS X, that's an excellent book to know about how it works. If you use Linux, that's a good book to know about Linux. I couldn't find such a good book for Microsoft OS in terms of what the kernel does and stuff. Right? I do have the source code for the different operating systems, Microsoft and Mac and all those things, which I'll put online. Some of them you cannot freely distribute, like the Microsoft operating systems you cannot freely distribute, but you can take a look at it to see what goes on underneath under the hood. So you have to buy the textbook, or figure out a way to have access to it. And I apologize, I don't know why it's getting so expensive. So here's my crude attempt at drawing some graphics. So the notion of operating system, right? So there are 2 different components. One on the corner over there, which is the hardware. You go to architecture class or something, you learn about hardware. So in terms of a machine, some of the figures I have here are the processor, memory, hard disk, keyboards, what have you. All the things that go into the computer that you buy, right? So those are the inanimate things that you buy. You kind of have all those things. that's what the architecture folks try to make it faster, make it whatever for the architecture part, right? Then you have the application part, which you probably used in your programming classes or you do use in everyday life, right? So you have this abstract concept of something called the PowerPoint. I didn't purposely put what's inside the media and all because that means that there is OS getting involved in doing some things. But for now, the concept is I want to use this bunch of hardware to do something. I want to use this bunch of hardware to use my PowerPoint or what have you to do something. Like for example, put something on the screen, print something, or what have you. I want to use these hardware, right? And the glue which binds these two is the operating system, right? So in terms of the core courses that you learn, some of the other cores you can kind of ignore. Some of the other topics, even though they're very important, you may go through life without ever having to go back to them, right? Not saying anything bad about them. So for example, if you take a course in compilers, right? If you became a surgeon or something, you're probably not going to learn about or deal with the compilers that much. Operating systems, you get frustrated most of the time because some of the things that you want to do, you can't do because you buy this hardware, the operating system is the one which makes the hardware do whatever you want to do. So it can make it look good or it can make it terrible, like what we went through, right? How many of you have been frustrated with any of the OSs that you've used and it did stuff that you didn't think it should do, right? How many of you? I'm surprised that a few people are. Okay, other question. How many of you were not angry with their PCs and stuff? Okay, so that's what I figured. So how many of you use, what operating systems do you use on a daily basis? How many of you use Windows? Mac? Linux? Okay, so I guess most of you use Windows, but few of you use the Unix variant. Unfortunately, I can't talk too much about Windows because they don't actually expose what they do under the hood as much as the other ones, right? So in the class, I'm going to talk about Mac OS X or the Linux a lot more than Microsoft OS. Not because I don't really like them, but because they like to talk about the GUI and all the front end stuff, not the core of what happens underneath, right? So that's where the operating system comes in. So to put it in a more textual format, if you think of a machine or a computer that you want to use as 4 different things, like it involves the hardware, it involves the user, you, and it involves the applications, things that you want to do with these machines. Operating system is the one which kind of connects all this stuff. So in terms of hardware, you have processor and memory, I/O, keyboard, mouse, tape, DVD, whatever, printers and all those things. In terms of users, it could be it could be other machines. For example, when this machine comes up, if you notice, it talks to a whole bunch of machines to get some services, right? So for those machines, this is a user. So when I say user, it could be real people or it could be other computers that get services from. And in terms of applications, the sort of things that you have used, word processor, compiler, web browser, databases, video games, and all those things, right? So to define, in terms of how your book talks about it, operating system is an intermediary which makes sure that the right application gets the right resources. So if you think of printer as a resource, operating system is the one which makes sure that your PowerPoint gets access to the printer or what have you. So in that sense, operating system is a resource allocator, right? So it figures out there are multiple applications, multiple users, multiple stuff, and it gives each one of them what they require. And it also is the one which controls how much they should get. So it wants to make sure that not only does it give it to you, it also takes it back from you if you're abusing it, right? So when you're done with it, it takes it back. So it controls everything. So if you want a printer, you have to go to the operating system, and based on some policies, which is what we'll study in the lecture in the classes, it decides that you should have something. So if it decides that you should have the screen, it gives it to you. And if it decides that you are abusing it, or if you're going over, or if you're done, it takes it back and cleans it away, right? To make it more concrete, if you notice, right now there is a Internet Explorer running under this machine, right? So if you're doing a PowerPoint slide, there's an Internet Explorer running in the background, and it has no access to the screen, right? Right now the screen is fully taken over by the PowerPoint. Operating system is the one which decided that this PowerPoint application should get the whole screen, right? Which means that the IE, which is inside, doesn't have any access to the screen, so it decided that that's the right thing to do. And at some point, it's the one which decides, okay, you're done with the PowerPoint, now I'm going to take it back, clean up the screen, and let the Internet Explorer run, and it gets its services, right? So that's, in a nutshell, what the OS does. If it does it right, you are happy. If it does it bad, you are unhappy, right? And the way it does it bad, no operating system does things bad because it wants to. I mean, it doesn't do it maliciously. It just does it because it's not what it doesn't expect what you're trying to do, right? And as we go along, we'll see what that means, right? So, for example, this desktop operating system, it's designed to give whoever is on the front of the computer all the resources that it wants, right? So right now the IE is being denied of all its services, but that's okay, nobody complains, right? And this is not what you would want for a server. This is not what you would want for some other place where you run your operating system, right? So there are a lot of examples of why things are going, why we need to study about operating system. One other thing is, this is input-output device, right? I'm trying to talk to this computer through this thing, and it's not giving me priority, right? Oh. Okay. So at a high level, your PCs have some sort of a bus. How many of you built a PC on your own? How many of you gone inside and looked at some of the hardware components? Wow, that's pretty good. So you may have realized that there's a bus. You have all these components like your CPU, disk, and mouse, keyboard, printer, monitor, and all those things, right? So you want to make these things go as fast, right? So for example, what happens if you look at this architecture is there's a lot of input coming into the machine asking for service, right? For example, I'm mashing this button to say go to the next screen, and there's a lot of output going out of the system, like for example on the screen, right? And everything has to go through CPU, which is out of the brain, right? So if you connect them directly, forget for a moment that the disk controller, USB controller, all those things are not there, right? Which means that everything has to go to the computer. So when I press this stuff, somebody has to tell the CPU has to do what it wants for me, every little thing. So for example, if you think of a printer, right? If I'm printing out every character, it has to go and the CPU has to send one character, goes to the printer, it prints it, and when it's done, you go back to the CPU, gets the next byte of memory from somewhere from memory, do it, and so on, right? And if you do that, it gets to be very slow because the CPU is constantly working on I/O, it's constantly doing all this stuff. So to make things go faster, you have this notion of device controllers, right? So essentially, they are little computers on their own. So what you do is, rather than talking to the disk, rather than talking to the keyboard or whatever, the OS talks to the disk controller, and it says, go ahead and read some amount of data, and then tell me when you're done, right? So that way, things can go in parallel, or what we call as concurrent, right? So to the extent possible, these things are going parallelly because the CPU is not directly talking to each of those stuff. It talks to these controllers, and the controllers do work on behalf of the OS, and when they're done, they get back, right? That's one way to speed things up. So rather than sending each character to the printer, rather than worrying about if the printer is jammed or whatever, the CPU does not get involved unless there's some error, unless something cannot be done by the driver, right? So you have all sorts of drivers in the machine. So when an operating system manages stuff, it says, okay, I'm going to give you this controller. I'm going to tell you this job to do. You go off and do whatever you have to do. And if you have a problem, if you're done, then let me know, right? And doing that makes things go faster because now the CPU can juggle all these things. You can say, CPU you do this, and graphics card you do this, printer you do this, and all of them are doing their stuff. The CPU could be doing other calculations, other computations.
They're getting a little bit below the sensor.
Good. Okay. So this is what we call offloading. So whenever I have to do some work, I offload the work to the device controller, and the device controller goes off and do something. So think of it as your secretary, right? I'm guessing most of you don't have a personal secretary. Neither do I. But if you had one, you basically say, I want 40 copies of this, give it to the secretary, and they go off and do stuff. They have to worry about changing the printer or changing the paper, what have you. And then essentially when they're done, they want to come back and say, here you have the copy, or they say, the printer burnt down, so you can't have a copy or something. So things that they can't deal with, so they tell you, right? They don't come back and say the printer ran out of, there's no paper, there's no toner. You just say go back and fix those, right? So that's the idea. So to do that, you have to have buffers, right? You don't want to give like every little work. So you have what are called buffers or caches or what have you per device. So I can say, rather than giving one byte at a time, I can give a chunk of work. I can say, go read a whole bunch of stuff, go write a whole bunch of stuff, go print a whole bunch of stuff. And when they're done, they fill that buffer, right? So if you think of this abstractly, you have the CPU, which if it wants to interact with the device, put something into the buffer, right? And say, go read some contents or go whatever. And then when the device is doing its work, it puts the data back in the cache. And when they're done, it has to tell the CPU, hey, I'm done, now you can take the results. And the way it tells you when it's done is through interrupts, what is called interrupts, right? Basically, it's a hardware mechanism to tell the CPU, wake up, now we have the results you want, and then you proceed, right? So when you take the architecture course, you'll learn about how to create this hardware interrupts and what's the signals and all you do. From our perspective, somehow the CPU gets to know that there's something happened, and the CPU goes ahead and deals with those, right? So that brings up the issue of, so now that the CPU is delegating work to other units, right? It can potentially be sitting idle and doing nothing, right? So if you want to get the most bang out of your machine, you want the processor to do something else while somebody's doing the I/O, right? So when you tell the disk to read some things, and while you're waiting for the disk to finish reading, right, the processor is sitting there. So instead of sitting there idly waiting for the disk, right, you can do something else, right? And the something else depends. So for example, the basic stuff you can do is multi-programming, right? So the idea here is if you have more than one program, the OS can, when it's waiting for somebody to finish, it can go on to the next person and work on them, right? So while you're waiting for the printout to come, there's nothing you can do because you're waiting for the disk to be read. You go to another application and you make progress, right? And that's the basic notion of multi-programming, right? The whole idea here is you bought this nice machine with all these resources. If I use it very inefficiently, I will be doing one at a time. Everybody else is idle, right? If I want to keep all of them going, I have to have a notion of having multiple things to do. Since all these I'm relegating stuff to these IOs and other machines, I can make progress, right? You can't take it all the way because sometimes you have to wait, right? If you have two processors waiting for a printer, right, we have to do something about disambiguating those stuff. Otherwise, you could have two programs, each of them trying to print on the same printer, so you have half the printer from one, half from the other one, kind of interleaved, right? Probably not what you want. The ways we'll see how we can get around that. So, to the extent sometimes you can go, sometimes you have to stop, right? Can you think of another input device which you would exclusively use with one application or the other?
Keyboard?
Yeah, keyboard is an excellent example, right? You don't want two applications to be sharing the keyboard at the same time. It'll be pretty annoying for you to kind of type and then not know exactly where the input is going, right? So when two applications are requiring for keyboard, they have to stop. But if they're both computing pi to the nth degree or something, they can go off and keep making progress, right? So the idea of the multi-program idea basically says that once somebody once you're stopped because of I/O, you go on to the next application. If you take it to the extreme, where I keep switching, even though you have something to do, I keep switching really fast, right? You can make it look like all of them are running simultaneously, right? So the way you do that is if you have 3 of them do something, I let one person run for very small amount, let's say 10 milliseconds, right? You run for 10 milliseconds, you run for 10 milliseconds, you run for 10 milliseconds, and I keep switching, right? If I do it right, all of them gets 1/3 of the CPU. They get to run 1/3 of the time, right? So if you look at it cumulatively, you're running only 1/3 as fast as if you have the whole machine to yourself. But if you're doing interactive jobs, you hardly notice it, right? So you hardly notice it because you're not doing CPU tasks all the time. So if I keep switching, if I do it right, you won't notice that you don't have the CPU with you all the time, right? And that's what all these machines do, right? So if I have the IE running on the background and I run PowerPoint on the front, it's not like they magically get this entire CPU. They're already running half as fast as what they would have done if they were running exclusively, right? But for the most part, you don't really care because it's juggling fast enough. It's doing such a good job that for the most part you don't feel the pain, right? You feel the pain if one of the processors get the CPU and holds on to it, right? And that's when you see spinning balls or depending on the operating system, some way to say you're not getting any CPU because the other one has all the stuff and you're kind of stuck and you're trying to reboot the machine because you're not getting your CPU, right? But if you are running normally, it's doing this juggling so fast that they're all happy, right? And there are other abstractions that we will study as we go along. So these are different techniques to make the task I'm talking about go faster. But remember, the fundamental thing you're trying to do is you have a set of resources that you're trying to give to different people. You are trying to make these things go so nicely that everybody's sort of happy, right? There's really no magic. So one of the things that you want to remember in the operating system is, even though your book talks about some of the techniques, none of them are set in stone. None of them are definite truths. They all depend on what it has to do, right? And hopefully that's one of the things that you will take away from this class, because that's one thing which is going to affect what you're trying to do, right? And that's hopefully what I want to bring to the table, to give you a perspective, right? How many of you bought a machine recently which is fairly decent? How many of you have a dual core or quad core machine of those? How many of you know what that is? Oh, hey, that's excellent, right? So essentially, most of you seem to know what dual core and quad core is. Dual core and quad core, in abstractly, it means that it seems like you have 2 CPUs, right? So now you have 2 CPUs to do the task of one CPU, right? So a simple way to look at that is just think of what we were doing before, trying to do this juggling. Now I have 2 CPUs to juggle all my tasks, right? So I can go that route. But what it also enables you to say is, so now that I have 2 CPUs, I don't have to be so conservative about my allocation, right? I can just give one of the cores to do some task, right? Even though it's not the right things that we would want to do, we just want to do it because we can, right? And those sort of things, the book won't talk about it, but that is happening all the time, right? So the idea here is I have 4 cores, right? So I can give 1 core to the PowerPoint, right? Which means that the PowerPoint core is always there on my beck and call. I would never lose the PowerPoint core, right? It's not the most efficient way because right now I'm not touching anything, so right now the machine is not doing anything. But I don't care because even though I'm not touching anything, this machine right now is all the thing that it's trying to do is service me for my PowerPoint, right? So I want to give it 1 core, even though it's not the right thing to do, even though you may disagree with it, I don't really care because I want it for me, right? That sort of thing you couldn't do before, right? And that sort of thing you'll see in the future. So hopefully you'll understand enough of operating system to know what is possible and what is the goal, right? And like I said, the management goals depends on what you're trying to do, and that's what they should enable, right? So there are a number of different things you'll see here, which will look at throughout the course. There's the notion of, so what happens? So you have PowerPoint, how does it show up on the machine, right? You have an abstraction called process, right? How do you manage this? How do you allocate resources? How do you manage this process abstraction? It would be something called process management. Then you have memory, then you have storage. How do you manage memory? How do you allocate memory? How do you allocate storage? How do you manage storage? Those are, and we'll see something like virtual memory and all those things, right? And I put them in blue because we'll see that in a little bit why we're going to do that, right? So one of the other things we kind of left out was, since OS controls everything, it has to be protected, right? If you don't protect it, then what prevents you from everybody from asking the best, right? So in terms of the PowerPoint, OS decides that PowerPoint should be the one who's running right now, right? IE can get, I don't want to be left out, so I want to take control. I want to take over the screen, right? So the OS, if it wants to give privileges, it has to be able to do stuff that the normal processors cannot do, right? Otherwise, everybody can just take over and everybody can run the show. So usually you have a notion of a dual mode. You have a kernel mode and a user mode, right? So there are mechanisms where how you elevate yourself from normal to a kernel mode, and so once you're in kernel mode, you can do anything. You can give allocate, you can change some tables and stuff. As a normal process, you can't, right? So that's the way to say, if you want some resource, if you want a hardware, you can't directly do it. You have to elevate your privilege to the kernel, ask the kernel, can I do that? And if the kernel wants to give it to you, it'll give it to you, and then it'll take it back, right? So normal processors run in user mode. They don't have the privileges to do stuff. You have to control how this switching happens back and forth. Otherwise, this whole system will disintegrate, right? And so we'll see the protection structure later on in the class. So some of the operating systems, most of you seem to use the desktop operating systems, Windows, Mac, or Linux, and variants of those. And there are other operating systems. There are operating systems for servers, right? And essentially, all they're trying to do is, depending on what you're trying to do, the goals are different, but basically they're trying to do the same thing. They all have a CPU, some I/O, input output they want to deal with, and depending on what the functionality is, they manage them differently, right? There are also another class of applications, embedded and real-time systems, right? And the applications, the OS for those are QNX, VxWorks. Some of you may have heard of those, right? These are operating systems which run on embedded devices. They run on other devices trying to manage stuff. So, for example, this camcorder probably has operating system which is trying to figure out, it's doing the I/O. It's capturing a video. It's storing something. So it's doing whatever its task is, right? So your cell phones, your washing machines, your nuclear plants, and all those things have an operating system which essentially do the same sort of stuff, right? And some of them have real hard deadlines. So, for example, if you're running a nuclear power plant, right? And if the nuclear power plant is about to blow, there's a catastrophe happening right there, and somebody's playing solitaire, right? On the console, it's conceivable, right? So, in that sense, what it should do, how it should allocate resources, are a lot more serious than what happens here, right? For example, if the IE comes up right here, at the worst it happens is, I'm kind of unhappy that IE came up, I just go back, right? Not the same with nuclear power plant, right? Not the same with your car. Most of your car is controlled by embedded operating system, right? When you apply the brakes, if the machine says, nah, that'll wait, let me show you what the temperature is outside, right? You're not gonna like that. So those machines, they even though they do the same kinds of stuff, even though they're managing stuff, they're managing input I/O, input output, right? The consequences drive what they have to do, right? Those machines don't really care what you do. If you apply the brakes, everything else off, it has to do those things. And those are the notions of real-time systems, right? We're not going to talk about that particular stuff because there's a separate course talking about how you go about doing this stuff, right? There are a lot of courses that you will see in your senior year which builds off of many of these courses, And I'm not going to touch go into those topics because they have a separate course. They're going to talk about those. So I'm not going to talk about these things. The thing to remember, there are a lot more of them than us, right? There are a lot more of embedded systems than operating system for desktops and stuff, right? I'm guessing most of you have a cell phone. Most of you have other little devices which are running operating system, right? I think there are like 10 times or some odd number more embedded systems than OS. So it's not that they're not important, it's just that there's a separate course to deal with the nuances. We'll focus on the desktop server kind of machines. This is like an art. So that's the course goal. I mean, this is the core course. I'm assuming that whether you like it or not, you are here. So let's make the most of it. I want to give you a sense of what the operating systems are, because I feel that you will run into this. Whatever you do, you're going to deal with the machine. So when the machine is not doing what you want, you have to be able to understand why it's not doing what you want, right? Other than being malicious, what you have to do to make your programs faster, what you have to do to make the things go faster and stuff. So this is something that you will face all the time. So hopefully we'll get into that, and I'll go more into breadth rather than depth, mostly because depth depends on what you're trying to talk about. So if you're talking about desktop operating systems, the depth will tell you have to do these things. If you're talking about server operating systems, things are different. Talking about different classes, things are different. And I'll try to give as much hands-on experience as possible. So we'll have course projects, and the scope of the projects are such that it's not too much work, but I'll let you try some of these things. Right? For example, look at the source code of the different operating systems and stuff. And hopefully the projects will help. Right? And we'll follow the text for the most part. And I expect you to read the chapter before you come to class, so we can go on and see how it applies to modern machines kind of stuff. So I'll talk more about what this means and how the world is moving. And if you find anything interesting in the literature or in the news items, bring it to class, and we'll talk about what that means, right? How many of you seen like the iPhone, Apple iPhone buzz about it, right? So I mean, to me it's cool because it's running operating system, it's doing the sort of stuff that are interesting to look at, right? So one of the hardest part with teaching the OS class in my mind is we will talk about different components and how they manage their own resources, right? It's important to remember that they're all trying to manage what was given to them and how to shuffle them so that they can keep them all busy, right? But in terms of what you talk about, they are different. So for example, when you talk about process, you talk about scheduling. When you talk about disk, you talk about scheduling. When you talk about other things, you talk about scheduling, which essentially says who should have the disk, who should have the process, who should have this stuff, and then move around. And the specific way you do that depends on the kind of medium, right? The processors are not that many, they're fast, disks are slow. So you change some things, but they're still the same, right? So in order to prevent any kind of confusion, I'm going to split the class into basically 5 different subclasses, right? There's a process management, synchronization, memory management, storage management, and protection, security, and all those things. And kind of have their own little exams, own little projects, own little assignments. And some of the topics we have other classes in the grad or under senior level classes which go more into detail of those. So we'll have 5 exams, 5 model exams. The schedule is on the web page. We'll have one final exam which carries a 10% of the grade. Most of the other ones are small grades, right? So and then you have 5 assignments and 5 homework projects. The implications of this is you'll have constant work throughout the class, right? The other component is it's very hard for you to do poorly, right? Because since I have so many data points, for you to say, so if you get a B for the last 5 projects and last 5 assignments, last 5 exams, and the final, right? It's very hard for you to say, I didn't see it coming, right? Because you die slowly, right? But on the other hand, if you had a bad day and then you got to be on 1, it probably won't kill you because you have other stuff, right? So that's what we'll have.
Yeah, are the quizzes going to be announced in class, or will we talk with
Pop quizzes. Yeah, the quizzes, I didn't have it last year. It's basically for you to read the textbook before you come to class. So it's only worth 2%, 1 per module. I'll randomly choose one day. And there are 40 of you in one TA. So I'll probably choose multiple choice or true or false time of question. So it's easier for him to grade, right? So there are many small things. So the projects, I can't really make you do a whole big project because each one of them is only worth 5%. You only have few classes, right? So the exams are in class, open book, open notes, but individual work, right? So you're free to bring your own books and notes or bring your laptops or whatever. You can't search for the answers on Google, but if you have the notes online somewhere, you're free to look at them, right? And one of the other things I like to do is make all the lectures, podcast them in video. So I think some people find it useful. It's a tool to kind of review it, and especially if you can't make it to class, it's kind of to look at the stuff. So you're free to bring those to look at them. You're not free to talk to your friends, right? And take-home assignments. They're basically trying to get you to do the exam. It's take home. You work on them. You may have to do some little experiments to answer them, and they're individual effort, right? The course projects, class of this size, ideally I would like two students per project, right? If you want to have more, a bigger group, talk to me. I don't want single person projects, right? And ideally a project would be, if one of you are good in programming and one of you is not, that'll be ideal kind of system. You can learn from each other, right? So to the extent, some of the stuff that, some of the programming assignments we'll do, we have a separate lab for working on those. The Cushing lab, I'll give you the password and stuff in the next lecture to get in. Essentially, we have six machines and 2 servers. Two Itanium servers, which are $120,000 worth of servers, right? So the idea here is those machines are there for the class. You're free to do anything with them except to break them, right? So you're free to install OS. So if you say, I want to see how Solaris 10 works, I want to take over the machine, I want to install something, and the machine now doesn't boot in. It's all toast. That's fine, right? You're allowed to take, I want to see how well they stand against a sledgehammer and try. And more importantly, make sure that nobody else is doing the same thing. So you don't want to fight with each other, right? So if somebody is installing something, don't go take the CD out, put your CD and then, So I think sending email to say, I want to work on this machine is fine. The idea is most of this stuff you'll only learn if you try it out, right? So these machines are not being used for any other class. So you're free to do whatever. You have to compete with yourselves, not with anybody else, right? You're free to do anything else as long as it's not illegal, right? And I actually define illegal to be slightly vague. So if you want to try something which you don't really know if it's illegal, talk to me and we can explore those, right? Something which looks obviously illegal. Something if you say, I wanted to see how the president's machine, whether it's safe, right? I can't see why that would be legal. But if you want to say, you want to try testing it against my laptop, talk to me, we can work something out, right? So some of the policies I have on the web page, so essentially the reevaluation policy. So if I give you a partial credit, I think if I do multiple choice, there won't be a partial credit. But if there's a question where there's a partial credit, that's being done, with the whole class in mind. So if you want to question that, you have to give me proof why you think yours deserves more. So unless you prove that your answer is right, you can't say I got 60%, I think I deserve 70%, right? That's and it shouldn't be a problem because it's so kind of so many things that you hardly have to work on that. So no late submissions. I want all of them to be delivered by the class time. For the projects and stuff, make a hard copy and then bring it to class or drop it in my mailbox, right? I've had too many problems with PowerPoint or Word not printing the way you wanted or what have you. So it's best if you print it and then drop it off. So I think the Notre honor policy asked me to put the honor code in every exam and have you sign it, right? I'm not going to do that, right? I'm going to assume that none of you are going to cheat, right? I never had an undergrad cheat in my class. I can't say that for grads, but I never had an undergrad cheat in my class, right? So I would like to keep it that way. So I'm assuming that anything you turn in, you follow the rules, right? And if there is anything that you're not sure, write it down. Write down what you did, or talk to me. If you can talk to me or talk to the TA, write down what you thought, right? Because if you don't, then we are second guessing after the fact, and those are problematic, right? So the main thing I want to bring out is, I don't mind if each of you talk with each other, even for projects which are meant to be individual work, right? As long as you talk with each other and learn, that's okay. As long as you talk with each other and copy, that's not okay, right? So I picked up the Gilligan Island rule. So essentially what this says is, if you all want to solve the projects and use assignments, and you worked on something, you wrote on the board, you discussed, you figured out what it is, right? You're not allowed to take down what was written, right? You are supposed to go away and then do something else, and then write it in your own words, right? Don't all discuss everything, write down what was discussed, because then it's hard for me to know whether you really understood or there's somebody who knows what the answer was, they're writing the answer, you just copy, right? So that's the intent of all the things. If I say it's individual effort, that does not mean you cannot talk to each other, but if I pull you and say, what did you write here, you got to be able to answer it. You can't say, I don't know, I mean, we are all talking and they had the answer and I copied, right? That's cheating. If you learned, that's perfectly fine, right? And if you learned with a bunch of people, write down who you learned it with, right? I'm not going to take off points if you say I worked with 10 people, these are the people I worked with, and this is the answer. But I'll have a problem if you didn't specify who the other people are, then you end up with, 5 more minutes, right? So, is that the last slide? Oh, okay. So, are there any questions, concerns about this stuff? So for the next lecture, I expect you to read the next chapter from the book, right? Yeah. No, chapter 3, I think. So follow the web page which tells you what the chapters are, right? I won't change the orders. If I have to change, I'll send you an email. And if you finish the Krispy Kreme, I guess, right?